All right, we're here at Basics, Part 3. So far, we've learned distance, time, velocity, and acceleration. In our Part 1, we looked at mass, we looked at momentum, really sort of a value of that motion, kilogram meters per second, because momentum is mass times velocity. And we learned Newton's first law, or the law of inertia, and I've stated it in a very simple statement here that state of motion is changed by force. Now we'll get to force, and that is really the important, or rather I would say the most important aspect, because you'll start seeing a ton of problems which build on this concept of force. We get to work, we get to energy, we get to impulse. All of that will get built on these ideas that you'll learn here. So let's just get straight into what exactly force is. Now, if I use this term saying a state of motion, is changed by the application of force on an object, of course, if your velocity was 0, you need to start moving, there'd have to be a force that gets something to move. So let's look at the intuition behind it. If you have a light object and it was at rest, you could push it with just a little nudge. If you had a really, really heavy object, you just feel like you have to put in a lot more effort to get it to move. So that motion is changed means there's something there that affects that it has a relationship to the mass, and it also has a relationship to the velocity, like as we get something at rest to moving, or if something's really, really fast, if you had to stop it, goodness, you'd need a lot more effort or force. So there is a relationship between force and the motion, the value of motion, and that is best determined by momentum. So we'll use this intuition and define here what is called Newton's second law. And in 1792, in his Principia Mathematica, Newton effectively, the simplest translation to English, I think, would simply be that, he defined force to be in some way proportional to the change in motion, which is effectively the change in momentum. And we'll kind of build on that. We'll state it in a more simple term. But before we state the law, we'll try and identify this. We'll state here using green force just because it's a term, right? It's almost like saying it's proportional to change in momentum. And I'd like to state that in some way as saying, instead of writing a differential, I just state that as, again, in a very simple, or maybe delta P over time, if you will, right? Much more simpler way. Now, in reality, you'd find delta P by delta T, which is change in time. But since for the purposes of this video, time is really, a period between two instances, I'll write it this way, right? And I'll keep it in this form so you have an intuitive idea that, hey, if I need to make an effect to the motion, change it in some form, then that means I'm concerned with the change in the overall impact of that motion, which is dependent on the mass of the object and the speed by which it either increases or decreases, and it's all done with respect to time, right? So I'll kind of keep it in that form, right? And then I'll get back to our traditional convention here, and I'll define force. We'll do this here. This is important, and hopefully you catch this and stay with me on that. Force is typically defined uppercase F, and I'll write this as proportional to the rate of change of momentum. And if momentum is P, we know as mass times velocity. So I will now write that as change in mass times velocity, which is delta mass actually times velocity over time. Now in classical mechanics, we won't go to Einsteinian mechanics. In classical mechanics, for most observable and practical observable velocities and time, you don't see any change in mass. So mass is a constant. Proportionality, when you come to the metric system, becomes unit, single, one value. It takes in the metric system, because of the way the definitions of force and the units of its measure, the unit called Newton, this proportionality can be replaced by a constant value of 1, and mass remains constant. So what happens here is the proportionality becomes equal to, it's replaced by a constant. Normally you would have a constant k that would come in. I'll just write k here. Mass doesn't change. And you would get delta V by time. In the metric system, the definition of the unit of force as Newton, a force of 1 Newton means you would have K to be 1, right? And that's the way in which we kind of reverse engineer this unit or definition of the force as a Newton, but we'll get to this, right? And maybe to clarify, I'll also put in here, we know momentum and velocity, right? Momentum is basically, I'm going to go back to green. This is kilogram from the mass, meters per second comes here, right? We know that, right? When we bring this down here, and then here we know that this is divided by second, right? When we come down here, let's just make this, simplify this as writing this as kilogram meters per second square, if you will, right? Something looks interesting here, meter second square, acceleration. So if I want to define force and give it a unit called Newton, which is effectively in line with that, but to define 1 Newton, I will set K as equal to 1, right? So that's how I eliminate so force in newtons, maybe a better way, write it as force, F, in a measure Newton, when K is set to be 1, would simply be mass unit with a unit ratio, mass times acceleration, right? And by the definition of 1 Newton, that would bring these back into kilogram meters square. Force in Newton equal to mass times acceleration. You will find different definitions again. So second law originally talks about force being proportional and in the direction of the change of motion. That's how it's actually defined. But a lot of textbooks will simply bring the second law of motion down to force is equal to mass. Again, they would use a lowercase m and write Newton's second law in that manner, right? So that's the second law of motion, effectively bringing force to be equal to mass times acceleration. Acceleration is the change in velocity. So heavier the object, more force needed to get it to move or slow down, right? Or increase in its velocity. Or the faster you want to make an object move from rest, or the faster you want to slow it down, the more force you would need. And that's important that you understand force is measured in newtons, but the way in which a newton was defined is by setting this constant of proportionality to be one of unit value. Okay? So that brings us to force, and I'll leave this one there. Digest this. This is important because a lot of things that will continue from here will be based on this and Newton's second law. We'll see you in part 4 of basics.